we're going to get this party started and talk about that. So, hide this. Hide it. So, what I want you guys to understand about homework 2 is the following. And don't forget, in the big scheme of things, some of you did a lot of work on that, and some of you not so much. I mean, it's 5 points, right? And that's what the homework was for. It's 5 points. So, and I don't mean to make that in light of it. The point is twofold. You got to you know, if we take our little time machine and go back to the first day, second day of class, and we say, what is statistics? And we say it's this idea of collecting and analyzing data, right? So all homework 2 was basically about is basically saying, listen, we want you to be able to somehow realize that collecting data is usually not easy. It's a pain, there's a learning curve to it. Analyzing data is usually going to turn out to be also a pain and a learning curve until you learn how to utilize certain things. For example, software, or what I said is trying to use Excel. But the even bigger picture is, and this actually, I think, Katie, if you're on there, I don't remember if you are or not, let's just assume you are, goes to your question. Even if you manage to figure out how to make a frequency table, even if you manage to know how to compute the mean in the median, even if you manage how to do all that stuff I asked you to do, what good does it make? What did you learn from it? Can you make any sort of, can you learn anything from it? So the purpose of homework 2 was to get you to understand there is so much we don't know. How to do. And that's okay. So don't get frustrated. Don't get overwhelmed. Don't get mad. Don't get annoyed. There are so many things, and we could talk about this, from how do I find data on the internet, right? For one. Not only that, how do I put my data in places that I can try to learn from? And then even if you do make pretty pictures and charts, what does a couple boxes mean? This says this, what does it mean? How is it useful in any sense of the word? And so a great way of pointing this out would be if you look at homework 2 problem. Give me 1 second, I have to pull it up. So I think it would be the last problem. Okay, so not even the last problem. You know, let's look at problem 6, for example. You know, again, I say go to Google machine, find the 50 longest rivers, whatever. Let's look at their means and their variances and all that. Make some pictures. And then for number 7, we did twofold. I didn't ask you just to collect one piece of data on something. I asked you to do 2 things. Right? And so the common question that comes from you guys was, well, what do I do with it? That's the whole point. I didn't tell you what to do with it. It's up to you, right? What can you do to it to get information out of it? So for example, you might take, I said, go to these cities and find their height above sea level, and then find their latitude and then their average temperature. And then the idea is maybe you can make conclusions. And there's these words you may have heard, but maybe we've never defined them. Things like causation, things like correlation. Is it just because you're close to the equator that you have to have warm temperatures? Well, what if your altitude's higher, right? We always associate high altitude with cooler temperatures. We always associate being closer to the equator with warmer temperatures. So is basically a problem like this, there's no right or wrong. It's not like you can turn something in and I say, this is stupid. This is poor analysis. That's not the purpose of this. The purpose is for you to think and ask questions like, what am I supposed to do? And then once you make some table, then ask yourself, okay, can I learn anything from this? Did I learn anything from the data? Is it true that cities that are at this latitude have similar temperatures? Why or why not? Is it true that those at this height above sea level have similar temperatures? Why or why not? And not only why or why not, can you conclude that? Now, you get confused about a problem like that. Every semester, all the students do. You say, I don't know what you want from me. I don't know. And that's the point. Go all the way back to one of the first things I said to you guys in the first day of class. And I said, what does it mean when the weather report says there's a 30% chance of rain? What does it mean? You don't know. Hell, Jeff Rosilla might not even know what it means, but he'll tell you. And people watch the news all the time and say, okay, I better make plans to go outside. There's only a 20% chance of rain. I'm okay. Even though we really don't even know what that means. We just mean, maybe intuitively we think 20 is good if we want sun, right? Or at least not wet. And we would think like 80 is bad. But I'll give you a great example of this. Yesterday morning, I was in a golf outing. All day Saturday, they said it's going to be a washout. It's going to rain all morning, torrential downpours. And that's what the forecast was in Pennsylvania or Western PA. But guess what? We got rained on for 20 minutes. And that was it. Now, other parts of the city were getting pummeled with rain all morning. But we got rained on for 20 minutes. So if I'm sitting in southeastern Allegheny County and I'm watching the weather report that says there's an 85% chance of rain all morning, and someone who's sitting up here an hour away, up in McCandless is watching the same weather report, clearly McCandless didn't experience the same weather that I experienced yesterday. Now, does that mean that the weather people are stupid? No. Does that mean that they don't know how to use the information that's given to them? No. But the fact of the matter is, it would be impossible for them to give every single person, depending on where they're living in Pittsburgh area, an accurate forecast. It just doesn't make sense to even assume that can happen, right? So if I can reemphasize this one more time, it's not so much about what is right or wrong on this homework in the big scheme. It's about what can you learn. Did you learn anything new now? Can you make a chart on Excel? If you could, you got success out of this. Can you get Excel to find the mean of 50 numbers? If you can do that, great. Now, I don't care where you get your 50 numbers for the 50 longest rivers. All I care about is that you calculated the mean of them correctly. Whether you got maybe you got information from a different web page or a different source, and maybe yours is right, mine is wrong type thing. Does that make, or not right, there's no right or wrong, but maybe we're taking the mean of 50 different numbers. Can you go to the internet and collect data? Now, we haven't even asked you the thing about how do you cite data correctly yet. I mean, who knows? Are you any more capable today than you were 3 weeks ago with Excel? Even if it's just a little bit, that's good. Even if you've watched one video, that's good. No one is asking you, I am just trying to sort of give you, what's that old little phrase? If you give a man a fish, he eats forever. Man, the fish he eats forever. One of those old proverbs or something. That's what I'm trying to think about with this. Your goal is not to have some perfect homework too right now in September. Your goal in December is to look back and say, man, knowing what I know now, here's perhaps how I would have done this homework. That kind of thing. So in many ways, this homework is trying to show you, here's lots of skills you might not have, or lots of things you're not certain about, or you don't feel comfortable doing. And hopefully that will encourage you to want to get better at that stuff. Now, maybe it will, maybe it won't, I don't know. And it's not a bad thing. You can ignore this homework for 5 points and still get an A in the class, probably, right? But it's more or less me sort of giving you sort of, here's some stuff, go out and play with it. It's like a toy box. And if you learn something, great. If you don't, that's fine. Does anybody have a question about that? What I mean by that? I mean, don't forget too, one of the original examples we talked about is this idea of what is the average height of an adult on this planet? What if I said to you, I want you to do that experiment on your own, Now, clearly, I'm not expecting you to go out and measure people, but how would you maybe say, okay, where could I go on the internet to get data about heights? If there even is a place. Do I go to like the National Institute of, is there some place on the internet where I can get data of it? Who knows, maybe there is, maybe there isn't. So another way to think about this homework is along that lines where, okay, if I want to learn something, if I want to get information, where's the first place that I go? I always found that counterintuitive, and I don't know if it's still this way, but even like 10 years ago when students would always come to me and they'd say, well, Dr. O'Grady, our teachers in high school said we're not supposed to use Google and we're not supposed to use Wikipedia. And I'm like, why the hell would they tell you that? Like, if I don't know something, the first place I go? Google. What's wrong with Wikipedia? There's sources everywhere. I don't understand why people are against Wikipedia. It's like they want you to march to a library just because they had to do it. Right? So I want you to be cognizant, though, of where do you get your information from. You might say, well, what's he talking about? He asked us to get free throw percentages and rivers. That's not the point. I just randomly picked those things. Why did I find the payrolls of NFL? I don't know, because I'm listening to the radio and everybody's excited football started. I'm like, I like football. Let's talk about football. Right? Then I have to be equal opportunity, so I can't say NBA free throws. I say WNBA free throws. Now everybody's happy, right? And we do rivers so that the geology people geology, is that it? I don't know. Who studies the earth? Geology? They're happy now. Then we give everybody, no matter where you're out in the world, we say, hey, let's look at all these famous cities. Sydney, Australia, where it's currently going into summer soon, right? Because they're the opposite of us, right? The southern hemisphere right now is in spring. Or no, because we're still in summer, so it's winter down there. And this is so cute how it works. Okay, so before we move on, does anybody want to say anything at all about homework 2? And if you thought it was a bad experience, that's fine. I'm not going to be mad at you. I would encourage you, though, to spend some time reading chapters 1, 2, and 3 in your book. Now, don't forget, I want to make this clear how I told you this class is going to go. I told you we're not going to spend a ton of time beating down all those things in chapters 1, 2, and 3. We hit a couple of the things that are important, but in my opinion, that's not the correct way to do it. You need to understand the mathematics first before you go back and talk about all that stuff. And so what we're going to do starting today is we're going to start getting into the mathematics that is going to allow us to be better at analyzing data. So let's be clear. Things like means, that's nothing. That's arithmetic. That's just one thing that tells us how it's one piece of information about data. It could be useful, could not be useful. Standard deviation could be useful, could not be useful. Median could be useful, could not be useful. Now, visualizing is all. Okay, a picture is always exciting. But if we really want to get at the ability to rigorously and carefully analyze data, we have to have a basic understanding of probability. We just have to. We have to. So that's sort of what we're going to transition to. And if you follow along in the book, that is what chapter 4 is all about. Chapter 4 is our sort of this book. And in most books at this level, we do a little bit of statistics and then jump into the probability, which is really the language that statistics needs to be read in and discussed in. And once we have a decent foundation of probability and what these things mean, then we can go back and talk about analyzing data. Does that make sense? So with that being said, we will start that as soon as we say, does anybody have a question, a comment? Everybody excited? It's Monday. Are you excited? Are you ready for the Steelers? I take it you're not. I'm not watching the NFL anymore. F them assholes. They make millions in this country and they don't appreciate it. You know I'm talking about those people. Yeah, F them. Anyhow, this is my favorite time of the year. I shouldn't say this being this will go on thing. My favorite holiday of the year is Thanksgiving. And I call it the hypocrisy of my most enjoyable holiday. And there's nothing better than like wearing shirts and insult old people who are assholes on like days like Thanksgiving. You get family together. I'll have to tell you all this. Some of you've heard these before. Like I believe you've heard some of my screamings about the hypocrisy of Thanksgiving. Do you like Thanksgiving? Yeah. You like it for the food. I like it for the food and the football and the beer. And then I also like it because it gets my family dynamic. You have a large group of people to get together of all different political opinions and all that. And it is so much fun to like have backhanded things to insult people. Of course, maybe that's rude, but I don't know. I'll say this. That'll be everybody. All those people. I'm not watching basketball anymore. Those athletes don't respect it. I love that. You make millions. Shut up. You know, favorite. Are people salty? Don't you wish you were a millionaire? I sure as hell do, right? Bitterness. All right, let's do some math. I'm in a good mood. Uh-oh, what's this? Okay, good. Party time. All right, so here's the O'Grady belief. Now, you might think I'm crazy. Well, I like talking about myself in the third person. This seems very arrogant, the O'Grady beliefs. So O'Grady believes I before E except after C. So that's how you spell believes, I believe. It's like I just got high or something all of a sudden. I don't even do drugs, but something just came over me. Like, are they pumping some sort of chemical in here? O'Grady believes the key to good data analysis is a solid understanding of probability. Now, what is probability? What is it? We've heard the word before. We use these ideas, but what is it? So I like to think is the branch of math that studies chance. That's how we like to think about it. Probability. So probability is a branch of math that dates back pretty much as far as almost any branch of math, because people have always been very happy and curious with things like games of chance, like gambling, and things of war, and lots of people who had things like kings and queens like to take advantage of those who didn't, so they'd have things like lotteries. We still do that today, right? That's everybody. We have casinos that people don't quite understand basic probability and give their money away to some other rich person. So what we'd like you to do is we'd like you to learn some basic probability so that hopefully you have a better understanding of how to handle data and information, and also make decisions when it comes to analyzing data. That's sort of the goal. Okay, so let's think about, the way I like to think about this is sort of through sort of scenarios. So let's play a game, very simple game. So to understand the basic ideas, let's play a game. Simple game. I toss a coin. Two times. So I'm gonna go with the assumption that everybody here understands what a coin is, right? Everybody, if I say heads or tails, everybody sort of has this idea, at least in the colloquial English, what that means. So we can record what happens. So it turns out there are 4 scenarios. So let's think about what they might be. It is possible that I get a heads and then I get a heads, correct? It is possible that I get a head, then a tail. It is possible that I get a tail or a head, then a head, excuse me. And then it's also possible I get 2 tails. So I'm using the capital letter T to represent that the result of my coin toss was a tail. I'm using the letter H to result that, hey, I got a head. So first off, we need to brace ourselves for the remainder of the semester talking about coin tosses and dice rolls a lot. And you're going to say, well, I didn't come to college to learn about dice rolls and coin tosses. And I'd say, yes, you did. You just didn't realize it. It's fun. Things like when we study heads and tails is just a very simplified version of lots of things in the real world. It either works or it doesn't work, right? I manufacture TV. It either lasts 10 years or it doesn't last 10 years. I sell you insurance. You either mess up and I have to pay you, or I don't have to pay you, right? You either live or you die. You're either on or you're off. There are lots of things that can be simplified down to a coin toss. A list of things that either do or do not happen. Success or failure. So one of the things that we do when we're trying to understand these ideas is we spend a lot of time talking about rolling dice, because that's an easy visual, and flipping coins. Every day I leave for work, I'm flipping a coin. I either make it home or I don't. I either make it to work or I don't, right? I either pay my bills or I don't. So there's lots of different ways we can do this. Does anybody have a question about what I mean by there are 4 scenarios? Of course, we're ignoring the fact that the coin will land on its side. We just assume that it'll land flat. It's either a heads or a tails. Now, suppose you can pay $1 to play. If you get at least 1 head, you win $1. If, or I shouldn't say if, otherwise, you lose your $1. So the natural question that you might ask yourself is, should you play? Now, from an intuitive standpoint, you might think, yeah, I should play. Or maybe you think, no, why would I play? You might say, I don't gamble. The math nerd said gambling is bad, or the lottery is made for people who are bad at math, right? That's one of the old jokes. But seriously, if you're thinking from an intuitive standpoint, should you play? Well, if we go back to the previous page, we say there's 4 scenarios, right? There's 4 things that can happen. And in 3 of those 4, I would win. Because I get at least ahead the first scenario, the second scenario, and the third scenario. So since 3 of the 4 scenarios are winning ones, my intuition suggests we should play. Now we're making lots of assumptions here, though. First off, we made the assumption that we can actually get ahead. What if I somehow concoct a coin that always is going to land tails? Well, then you're screwed, right? Now, if we assume that the coin is just as likely to be heads as it is tails, then it seems reasonable for us to play. I mean, we feel like if we, one way to think about this is we feel like if we played 4 times, we would win 3 times and lose 1 time. Does that make sense? That's one way to reason that there's 3 or 4 scenarios. That means then if we played 8 times, we might reason we're going to win 6 times. Or if we played the game more times, what happens to our chances of winning? So let's remind ourselves, of course, we are assuming that H and T are equally likely. Does anybody have a question? Yeah.
I think it's crazy how there's like the same amount of heads and tails, but it ends up being 3 to 4.
Well, but no, think about it. You got to be careful, though. I know what you're saying, but notice the operative word here is at least. So all I'm saying is, so here you get 2 heads, right? And then here you got 1. So this is a winner, this is a winner, and this is a winner, because all we're asking is that you get at least 1. But the point I was trying to make about if you keep playing the game more and more, it seems like your chances go down. I'm not saying they do. I'm saying intuitively it might seem that way. So one of the interesting things about simple sort of games like this, and this is what casinos understand very well, and people who run lotteries understand very well, is that all it takes is for a game to have a slight intuitive advantage. So obviously, we wouldn't be talking about this if there wasn't some sort of mathematical reasoning happening here that we're going to learn about. But what these casinos know, and what anybody who runs lotteries well know, that they know better than at least the players, is that our intuition can mislead us. And even if it just misleads us a little bit and we feel like we're winning certain times, or we're gaining an advantage, or we should play this game. What happens is in the long run, it turns out we shouldn't. And I alluded to this before. I think we talked about the simulation. Did I not? Did I show you guys the simulation when we talked about the dice earlier in the year? Where I said if you roll 2 dice, or you know, and then how many sixes, at least how many sixes. Our intuition misleads us because what we often think is that if we have more chances to win, then we should play. Well, the problem is the opposite is also there too. The more chances you have of winning also mean the more chances you have of losing. You know, you often hear this, people say, oh, you saw all this crap when the corona started. Well, we better not drive our car because we're more likely to do this. You know, people they conflate things, right? So people say, well, there's more people that die in car crashes every year than airplanes, so cars are safer than airplanes, for example. Or airplanes are safer, someone might argue. Well, the fact of the matter is there's way less people in an airplane every day than there are in a car. Also, it is very likely that if you're in an airplane crash, you are going to die. That's not necessarily the case if you're in an automobile accident. It's not almost a given that if you're in a car crash, you're going to die. Lots of people have small accidents all the time. So one of the things we misuse, whether it's on purpose or not, is we misuse our intuition. And then people who want to convince us of something, whether it's purposeful or not, often misuse statistics and probability to try to mislead you. So I don't know, and again, this is, if you ask me things that I would really like you guys as students to do, particularly in a class like this, is ponder these things. So there's a great story, this was a few months ago. There was a news report, a Tesla had caught fire. You know, one of those cars, and everybody, like all the people who were like mad at Tesla, they're like, look, these Teslas, you can't trust them, they're catching fire. And here's the thing, way more normal cars catch fire. It's just not a big deal, so no one reports it, right? But the way that the sort of the data is sort of portrayed to you, the consumer, is look at this Tesla, it's gotta be inherently dangerous. There's one on fire on the freeway, right? Meanwhile, you just don't see it on the 6 o'clock news necessarily that a normal car had an issue and the engine caught fire. Because it's, do you understand the point I'm trying to make? Maybe not. I don't know. Maybe I'm I'm confusing you more than we would hope. What do you think is more likely to happen? A traditional gasoline car catch fire on the road or a Tesla? That's a great problem you can ask yourself right now. You could probably Google that. Probably figure that out. Your intuition might say, well, there's way, way more normal gasoline engine cars. So that now that I think about it, it's probably more likely that those cars catch fire than, or there's more fires whose engine, or excuse me, more car whose engine catches fire than a Tesla or any other electrical car for that matter. Okay, so the bottom line is, in sort of, this is kind of the moral that we want to say is, how do we know for sure, or more importantly, is we need to develop a rigorous sort of system to determine how to analyze games such as the one above. I mean, our intuition is great and there's nothing wrong with using it, but how do we know? How do we know if our intuition is leading us in the right path or if it's going to fail us? You know, back to the car things. If you drive every day for an hour and a half versus someone who doesn't drive but maybe once a week for an hour and a half, who is more likely to be in a car accident? What does your intuition tell you? Do you ask questions immediately like, well, it depends on where they're driving. It depends on how fast they're going. It depends on weather conditions. Just like with this game, and I say, I'm going to flip a coin. Do I know that that coin is fair? Another good game to think about is the following. This is maybe familiar to you. Well, maybe some of you are familiar with a game like this. So take a plastic, I don't know, let's advertise for the Solo brands, the plastic red Solo cup. So for those of you who sort of don't know what I'm talking about, let's go to the internet. Everybody, that's a song, man. Oh my God. Everybody has seen a plastic cup before, right? I'm assuming at one point in time, you guys are like in your late teens, early 20s. I'm sure you ever play that game they call it Flip Cup, right? Where you're like, yeah, of course you have. Anyhow, one of the things that you've learned ever playing Flip Cup, whether you're drinking water or something else, is that cup is more likely to land on its side than it is either upside down or right side up. So let's draw our little cup. I'll even draw it red. This is so much fun. There we go. There's our cup. Let's toss it in the air. What are the scenarios? There are three sort of scenarios. And it's about time we start using real language. We call these things outcomes. What are the three scenarios? Scenario one, right side up. Like this, it is there. Number two, upside down. Or three, on its side. Those are the three scenarios that we could think about that. So your intuition tells you, and maybe your intuition doesn't, but if you've ever held a plastic cup and you can go home and do it for fun, throw it in the air, do it 10 times. Now, there was like that internet thing going on a few years ago. You guys would take like a water ball that would have some water in it and see if you can get it to land, right? Now, this game is a little different, though. It's not so intuitive for us to quantify how this game's going to go. So the point about the flipping the coin game is if we assume the coin is fair, we can in our head at least reasonably come up with some sort of quantities that we think is going to happen. We wrote it down. It seems to make sense to us that if three of the coin flips or three scenarios were winners and one was a loser, it seemed like it was a good idea. We could quantify that I'm going to win maybe. We haven't defined what this means yet, but you might say in your head, I'm going to win 75% of the time. You might reason that. And you'll say, well, 75 is better than half, so I should play. I got a good chance of winning. But if you notice this game, we can't quantify it as easily. At least there's no intuitiveness using numbers. We can't really say, well, if we assume that heads and tails are both 50%, then here's how it's going to go. And even if I knew a coin was sort of not fair, maybe I knew that maybe I went to a magician store and bought a coin that's 25% of the time is going to be heads and the other 75 will be tails. At least at that point, I can quantify it. But with this game, with just a cup, yeah, I can assume that there's not a lot of wind or whatever, but how can I quantify exactly how it's going to land? Now, in this game, our intuition tells us it's most likely going to land on its side. But that's only from experience, right? Experience tells us that, I think, if you've ever, with a cup. But if I just throw the cup in the air, is it like 33% chance upside down, 33% chance right side up, and 33% blah, blah, blah chance on its side? We don't know. And then we might say, oh, well, you know what? A cup's a little different than a coin. A coin, there's not much things that can change, but a cup, depending on what it's made of, if it's plastic, like O'Grady's talking, it might have one behavior. If it's a little thicker, if its bottom is thicker than its top, it might behave a little different. So there's a lot of other, what we say, variables happening here. I mean, I can take this can and throw it in the air. This can is probably going to behave differently than your plastic cup you have right there, which would probably behave differently than that plastic cup. So we see a game like this, which might be fun to play or analyze, or excuse me, to play is much more difficult to analyze than something like a coin flip. So then if you're creative, you might say, I got an idea, Grady. You might say, I will go to the store and I will buy a cup. And then I will sit up for 6 hours and I will toss a cup 100 times. And I'll collect my data. And I'll say, I'll record it, toss 1. And then I'll give it scenario 1, 2, or 3. Then I'll do toss 2, scenario 1, 2, 3. And then I'll do an experiment 100 times, 1,000 times. And then I'll look at my data and I will, from that data, decide, here's how likely it is to land right side up. Here's how likely it is to land upside down. That seems like a completely reasonable way to get information. Until you realize, well, maybe, just maybe, that ain't that good. Because here's what I know from experience. You could flip a coin 10 times and you might get 10 heads. You might get 10 tails. You might get 5 heads, 5 tails. You might get 7 heads and 3 tails. How many times would you have to flip your cup in order to get numbers that you think were valid, that they weren't skewed some way? A better way to think of it is if I said, you go home, and we should do this. This is what we should do on one of our homework assignments. If I said, Anthony, you take a cup and you do it 10 times. And I said, I'm going to do a cup and I'm going to do it 10 times. Chances are your outcomes don't look anything like mine. Well, that's not true. Maybe they won't. Maybe they will. In fact, actually, if you did it 10 times, what would you expect to happen? You'd probably expect 9 or 10 on its side. And I would expect that too. Just if we think intuitively. But if you did 100 times, would you expect it to be like 99 or 98 out of 100 on its side? So that becomes the next question then. If I want to analyze this game, how much time should I sort of spend thinking about quantifying these things? So let me reiterate that one more time. The coin toss game has not just intuition, but it also has a natural sort of way of us quantifying the scenarios, the outcomes. We know a coin, we can assume, at least we are pretty confident that some random quarter we have is going to be fair. Heads and tails are equally likely. So what we learn right away, same thing if we said we're going to use dice, and we imagine we have a die or 2 dice, each one has 6 sides. in our head, it's intuitive to us that, hey, each one of those rolls is equally likely as another one. I'm just as likely to roll a 2 as I am a 4, provided that the dice is made fair. And so at that point, I can quantify and get some sort of intuition on how any games with dice should be played or could be played. But I can't do that with this cup. And the reason for that is there's no natural way for me to quantify how likely one scenario is compared to the other. So what I'm trying to suggest is that there's two ways of thinking about probability. There is a theoretical way where we say, okay, here's what our intuition tells us, and here's what we can develop to back this up. There's a very natural way of doing things. Like we might naturally say, because this makes sense to us, we might naturally say, if I flip a coin, the probability that I get ahead is 50%. That makes sense to us, right? That seems like a reasonable thing to say, even if we don't really know what the word probability means yet. Or if I go back to this game, I might say the probability of me getting 2 heads in a row is 1/4. Why do I say that? Because there's 4 outcomes and one of them is 2 heads in a row. Just like I might say the probability of me getting at least 1 head is 3/4. At least that seems like, okay, that's a reasonable sentence to say. And we see some sort of quantitative reasoning behind that happening. But if I go to the cup game, there's nothing intuitive about me saying, well, it's going to land right side up. The probability it lands right side up is 22%. There's nothing that even remotely says, when I say that to you, there's nothing in your head that says, that makes sense. I can see that, right? Now, you might say I could see that, but there's nothing that convinces you that I'm not lying to you. So that doesn't mean we should just stop studying a game like this, but it means that we should think about it from a different perspective. Does anybody have a question or? Yes.
Is there a formula for this?
Oh, there's going to be, yeah. That's what we're building up to. There will be, well, not for the, there won't be a formula. So the question was, is there a formula for this? Now, let me answer that in 2 ways. There will be formulas for the dice games. There's not going to be a formula for the cup game. And that's one of the points we're trying to make is we're studying 2 different types of sort of experiments here. And what we're going to realize is that there's 2 different types of probability. The first game with the dice is what we would call, or is something that falls under the category of classical probability, something that we can quantify and study with formulas. The other thing, which is a category that the cup game comes under, is what we call empirical probability. Because I can't just give you a formula right now. How would I determine the nature of this cup game? I would actually have to play it lots and lots of times or have some sort of data on it to understand like the frequency at which it lands right side up or the frequency it lands upside down. And that might not make as much sense to you guys right now, but this is kind of what we're going to do. So let me maybe transition to it like this. So the 2 examples. Suggest there are 2 ways or 2 sort of to study probability. We'll call the first one classical probability, and we'll call the second one empirical. I guess I should spell empirical correct. It's I. And we'll get into this in a little more. We're going to spend most of our time, though, dealing with classical probability. So, a very common example here is, or one I like to use is because it gets fascinating stories. There are multiple types of blood types in humans. Does everybody understand that? So just a cool side note that one of the reasons lots of people died in operations years ago, and it wasn't that long ago, we've only known this for like 100 years or so, was that we would give us, during surgery, they'd give you the wrong blood. You'd die. So one of the issues we have now in, say, hospitals and other things, if there's an accident and we need to give you blood, we need to know how much, it would be nice to keep blood in storage that is going to be useful to us. Like, what is the most common blood type thing? Now, if I said to you, I'm going to pick a random person, I say, what's the probability that Billy has this type of blood? What's the only natural way we can maybe assign a probability to that? Well, one idea would be to take like 10,000 people and look at the blood types of 10,000 people or 100,000 people. And if so many of them have this type, we take that number divided by the total and we assign a probability in that way by observation. Whereas we don't have to do the same thing with a coin. If I have a coin, we can all agree that if we assume it's fair, then it's 50-50. Or if I have dice, every roll is 1 out of 12, right? There's 12 outcomes on a dice. Oh, actually, it's not true. How many outcomes there are on a dice? I lied, it's not 12. Well, let's just use one dice for now. A dice has 6 sides. We can all agree that 1 through 6, each one of them is equally likely. That seems like a natural way of quantifying it. But I know from experience that saying every blood type is equally likely, I know that's wrong. I know that from experience. Do we understand that? And since there's no way for me to sort of have an intuitive way of defining probability of blood type, the best I can do is think about what the empirical evidence suggests. And empirical is kind of like a fancy way of saying our observations in the past, our experiments. What have they led us to believe? We can go back to our height example that we've talked about numerous times now. I might say, given a random adult, what is the probability that they are 6'3" or taller? I mean, these are important questions people ask. They have to do that. If I design, if I make clothes, well, I'd like to know how many extra larges, double extra larges versus smalls and mediums I need to make. Does someone who make clothes, do they make the same amount of everything? Maybe they do, but maybe they don't. If I manufacture products, I need to know certain things like how big is my product? I need to know other things that maybe aren't so obvious if I want to ship them. Like if I'm making a product, what is the probability that everything I ship works? If I have a manufacturing line, I can't assume that everything that comes off my manufacturing line is not going to have issues. So these kinds of questions that are maybe not obvious to us at all, we often try to answer them in terms of things like probability. What is the probability that these batteries that I make are going to last for more than 10 hours? Now, again, these are questions that probably someone, and perhaps most of you fall under this, you've never thought about these things before. I encourage you to try to think about them. Ask yourself, why is probability important? O'Grady told us, let's flip coins and flip cups. It's not why I'm saying it's important. These are simple examples to help us learn things. But one reason you can go home with today to understand why probability is something that's important is because there are many very difficult questions that all over the world that people want to answer to. Chemists want to know, where's an electron at? Physicists might want to know something. Psychologists might want to know something. An MD might want to know, what is the probability of this medicine, or excuse me, will this medicine cure you? There are lots of very, very difficult questions. And one of the ways we found to try to attempt to answer them is to phrase them in terms of probability. Insurance agent says, what is the probability you're going to crash your car? And then they look at you and say, well, you're 23, so statistics show you're more likely than a 33-year-old, so you have to pay more insurance. So anytime we want to study the likelihood of something, whether it's going to rain, whether you're going to pay off your mortgage, whether you're going to drive to vacation or you're going to fly on vacation, anytime we want to know the likelihood of something, one way that we can try to quantify that likelihood and analyze it better is to phrase things in terms of probability. Yes?
There's one way to do it, like the amount of participants, like divided by the amount of like different things it matches up with. If you get what I'm saying. Let's say it's like a bottle, and how many different ways you can flip it? You can only flip like 2 or 3 ways. So you just like divide 1 by 3. Is that one way to do it?
Well, right, but that's only if they're equal. So the coin makes sense. You can say, okay, I have I have one coin. I'm going to flip a coin in the air. It's intuitive to us to say, okay, since there's 2 outcomes, you can define the probability as saying heads is 1/2, tails is 1/2. If I take a dice, 1 6-sided dice, and I say, okay, if this dice is made symmetrically, then each outcome should be the same. So you can say, okay, rolling a 3 should be 1/6. Rolling a 2 should be 1/6. Because there's 6 outcomes, we would assume they're all the same. So it seems natural to define their likelihood like that. Again, think about a dice. Think about the outcomes. Does everybody know what a dice is? Or a die, however you want to say. I think it's correct to say dice for 1, 2. If I roll a dice, there are 6 things that can happen. It can come up 1, 2, 3, 4, 5, 6. Now, if that dice, if it is manufactured properly, and let's assume it is, and it's symmetric, and it's like a cube, right? then we would assume that no one number is than the other, correct? Like there's nothing, unless we create the dice to be cheating, there's nothing that says a 4 is more likely than a 2. So what we do then is we naturally say, okay, so each one of the 6 things has the same likelihood of occurring. We just define it to be 1/6. And that is a very useful way of doing things, as we'll see. That is called classical probability. But I can't do that with the cup. You can't just assume that one of the 3 possibilities is a third. Because there's nothing about that cup, at least if we've ever taken a cup and thrown it in the air, that tells us that we're just as likely to get it right side up as we are on its side. And so just from that example alone, now that doesn't mean, look, you might be able to find a cup and manufacture one that they're all equally likely. But there's no way of saying that for every cup. You don't know that. So what maybe a better way to answer your question is to say some games, and I use the word game, you can think of an experiment. I don't know what kind of word you want to use. Some things have a natural quantitative association. A coin does. Why does a coin have a quantitative association? Because I can even go to this picture. Instead of tossing it once, I can toss it twice. And if I toss a coin twice, there are 4 possible things that can happen. That's it. Now, I'm not assuming that a bird's going to swoop down and eat the coin. I'm assuming that I flip the coin once and I record what I get. I either get a head or a tail. And then I flip it again and I record what I get. And then when I list down the 4 outcomes, there are 4 of them. You see them on the board. First scenario is I get 2 heads. Second scenario is I get a head, then a tail. Or I get a tail, then a head. And then lastly, the last scenario is I get 2 tails. There are no other options. And so then here, from what your question is, Phil, is now you're saying, okay, if I got 4 total, and I assume that flipping a coin is the same each time, then why not say that each one of these is 1 out of 4? Why not? We could be lying to you, but if we assume the coin is fair, it makes complete sense to say the first scenario is 1/4 chance. The second scenario is 1/4 chance. The third scenario is 1/4 chance. And the fourth scenario is 1/4 chance. Just as well, if I said, okay, then how many scenarios do you get at least 1 head? And there's 3 of those are the scenarios you get at least 1 head. And so then it seems reasonable to say, okay, well then the likelihood of getting the likelihood of getting at least 1 head is 3 out of 4. That makes sense. Now, right now you might be saying, it don't really make sense to me, but I think if you back up for a second and say of all the ways you can quantify this with numbers, remember, when I use the word quantify, that means associate a number with what you see. Yes?
I don't want to overcomplicate this question.
You're not overcomplicating. All questions are good.
If we're like trying to see what kind of blood type of person, like the probability of that they're going to get a certain blood type, we just like take the one person divided by like all the blood types.
Well, don't just say one person. No, you're close, but you're not. That's a better way of explaining it. So if I want to know the probability of, if I want to associate a numerical value with blood type, what I could do is I could survey, say, a lot of people, maybe 10,000. And I say, okay, if 300 of them have this type of blood type, then I take 300 over 1,000, and that can use that as my quantitative probability of how many people have that blood type. Does that make sense? Right. So yeah, you're absolutely right. And that's what I was trying to sort of make the point with the cup game. Since there's no intuitive way of assigning numbers, why don't we flip a cup 10,000 times? Right? Flip it. Right? See, now where does it land? So that's on its side, right? So you take a spreadsheet and you say, all right, side, and you count how many times it lands on its side. And then you count how many times it lands up, right side up, and then you count how many times it lands upside down. And then you take each one of those numbers, you'll have 3 of them, and you divide them both by 10,000. And that will give you the empirical probability that it lands on any given scenario. Now, the problem with defining things like that, and it's not a problem, is it just doesn't lend itself to a theoretical study the way a coin flip does. You know, just like imagine, and again, and it's not a bad, we're not overcomplicating. It's good to look at different examples. Here's what I go. I am a pharmaceutical company. I have developed a new pill to help someone who has some, I don't know, maybe some type of cancer. Right? I need to know if I'm a doctor who's going to prescribe this to patients, or if I'm a human who might take this. I want to know the success rate. Any new medicine probably comes with some sort of negative side effects, right? You've seen commercials before. I want to weigh, what should I take this new medicine? Is it beneficial to me? Do the benefits outweigh the risks? Now, there's no way of knowing. If I just create a new medicine, there's no way of knowing that it works 1 out of 6 times, right? There's no way. So what we can do is we can do studies. We say, okay, let's study 500 people that have taken this medicine. Did it work? Yes. Did it not work? Okay. Then we can define the probability that it works from that standpoint using empirical evidence. Does that make sense? So the game of flipping a cup, the new medicine, or the blood type, there is no way for us to define a probability in a classical sense. What we have to do is we have to use empirical evidence to determine what we think the probability is. Now, on that same flip side, suppose I start a gambling game with you and I say, I'm going to flip this coin, and turns out you're losing all the time. Well, then you might say, oh, Grady, that jerk took a quarter from the magic store that's not fair. And I devised a game so that I win. And so you might say, I want to make sure that quarter, I want to prove to the world that O'Grady is cheating me with this shady quarter. And so you go and you take that quarter and you go home and you spend 3 weeks and you flip it, say, 1,000 times a day. And at the end of 3 weeks, so that's 1,000 times a day times 21. So that's a lot of coin flips. And if you find that approximately half of those flips, right, weren't heads, then I'm probably cheating you. Now let that sink in your head. And these are things we'll talk about more. Suppose you flipped a coin 10,000 times. If it's fair, you would expect 5,000 heads. Not exactly, but roughly. Does that make sense? Let me say this again. If you flipped a coin 10,000 times and you counted all the heads, you would expect approximately 5,000, right? Because that's half of 10,000. But if you went and surveyed 10,000 human beings, you wouldn't expect that exactly half of them had the same blood type. Now, maybe they do, but you might not intuitively expect that. You understand what I mean by the difference between intuition and there's certain things that don't have an inherent numerical intuition. A coin flip has an inherent numerical intuition. Rolling a dice has an intuitive, inherent numerical side to it. Flipping a cup has an intuitive outcome. We think it's going to land on its side more, but we can't tell you, we can't quantify that unless we do some sort of experimenting. Does that make sense? Yeah.
So for the ones that have the set numerical outcomes, are those the ones that you can just like throw in like a division, or like, and the ones that you say like the flip cups,
yeah,
the ones that could go like anywhere with it, are those the ones that you have to like kind of write it out and try to?
Well, but it's not just write it out. So a better way to answer, or a better way to say that, I think, and not better way, not, but maybe this stuttering. A good way to think about it might be that what you said earlier. Certain things have this natural, a coin and rolling dice, it has a natural quantitative side to it. And so what that means is we can easily have formulas that say, okay, the probability of getting 2 heads out of 5 tosses is blah divided by blah, that kind of stuff. Or this other intuitive thing, if I have a drawer in my house and I have 3 black socks, pairs of black socks in there, and then I have 6 red socks, I don't know. You could imagine there's an intuitive thing. If you just reach in, how likely are you to grab a matching pair or 2 black? You just count. You count the options. That's an intuitive thing. But there's no numerical intuition about the cup. There's what's going to happen intuition. Intuition says it'll land on its side, but there's no intuition that it's going to be 30% of the time or 70% of the time. Now, your mind might say it's closer to 70, but who knows? We can't say for sure. And so that's okay. Like, you might say, well, why do we keep talking about this? Well, that's the point. Because what we're going to do is we're going to start by mostly studying the things we can quantify. And then we have to figure out a way later to use what we've learned about those games and those sort of things to help us answer more complicated things that we can't necessarily quantify. So I don't know. I hope that at least, if anything, I hope your mind is stimulated a little bit. You have questions. I mean, you ask some questions. That's good. Questions are good. That means you're curious. That means we're thinking. And we'll get into the nitty. I always like to do this. We'll do the ugly, not the ugly. We'll start doing the math stuff on Wednesday. But right now, we want you to ponder. I want you to really think about these games, the coin flip game and the flip cup game. And think about what I mean when I say numerical intuition versus not numerical intuition. Maybe I'm crazy. Maybe you're sitting there saying, what the hell does he mean numerical intuition? What I mean is, I think if I flip a coin in the air, in my head, I feel like half the time it's going to be heads and the other half it's going to be tails. So that means I have a numerical, intuitive idea about this problem. Whereas with the cup, when I throw it in the air, I say, hey, it's likely going to land on its side, but how likely, I don't know. Do we get that? All right, anyhow, go home. Thank you. Read some books, study, whatever. Be good to the people in the world around you, all that kind of stuff. Thank you guys for joining. I'll post a new homework, and that might help you see where we're going to go on Wednesday. Thanks, guys.